my best. Okay, so area under the curve. In a nutshell, area under the curve can be found through integration. So this is the proof. Yeah. Okay, so if we're going to call this A, this is x. And this is equation, we're going to call this point P, x comma f of x. We're going to find another point on the curve Q. We're going to label it, and it's going to be a distance of h away from x. So this is going to be x plus h. Oh, that's not very good. Okay, so this 10.1. So finding area under the curve. Okay, so this would be x plus h comma f of x plus h. Limits. Okay, so this here we're going to call the change of our area. From what, because from x, we've increased it. This would be our change of area. The area function, a of x, is uniquely determined by the position of point P on the curve, which makes sense, right? The area underneath is going to change based on where you are located. Now, select a point. I told you you have to boogie. I wasn't lying.
Oh, that looked like the same graph, but it's not. There we go.
Yep, just a little bit. Sure. Okay. That is close to P. Now, I exaggerated it, but we're actually wanted to be very close to P. Unfortunately, we don't have time to cover every chapter in every lesson in chapter 9, 10, and 11. There's some great stuff in there, stuff that you probably will cover in Calc and University. And we're just going to kind of sum it up in a few lessons. Okay, so then the area of the curved region, PQRS, so we're going to call this guy R and this guy S. Okay, so we have the region PQRS. I'm just going to draw a straight line here. So usually we use a trapezoid formula. I'm sorry. Okay, so PQRS is defined by that area, the limit as our change of x approaches 0, change of a over change of x, or limit as h approaches 0, a of x plus h minus a of x all over h. Would be the derivative. Yeah, first principles. So that's the derivative of our area. This change of a with respect to x would be the derivative of our area. So now, change of a, or change of area, would be area under x plus h minus area under x. Okay, so if you think about it as this area, take away this area, you'll be left with your change of area. Okay. So here, the change of area, so the area, we always to the x-axis, so the area under x plus h minus the area under x gives you your change of area. Okay, so in the big picture, this is what we're going to do. And we don't have time to really go into depth. Basically, what we're going to do is we want to take our curve and make it into very little tiny trapezoids. Super, super small trapezoids. Infinitely many. Because if I get the area and then I add them all up, we can get the exact area under our curve. Because it curves. And there's something called a left side area and right side area. So there's a trapezoid, and then you also could do from the left, from the right. So some are going to be above and some of them are going to be below. So trapezoid looks like that.
I thought trapezoids were the things that.
Yeah, Cody?
So we're finding the A.
I thought trapezoids.
Yeah,
the change of A in the next.
Yeah, so the idea is we want to make a whole bunch of little trapezoids. Right now, we're just proving our formula for the trapezoid area for this change of A, which we're actually going to make them as really small.
Why are we using that one and not the X? Like, why is it? Oh, that's what I want.
We have to compare it to something. So it's like when we introduce point Q on our tangent line. So we have to use we need to talk about what does this change of area mean, because we actually have to later on use it for lots of little change of areas to figure out our whole area underneath. So we're just writing a formula for the change of area right now. And then we want that.
We're not doing it on A of X?
Not really. Well, just this idea that we're going to get this right away, but we need to use that. We need to find change of area right now. Okay, so that's why I introduced a new point. Okay, so the change of area here is the area of the trapezoid, approximately, for secant area. Guys, we got 20 minutes to go through this lesson, so I really need you to stay with me. I know, because it's a insanely short day. Okay, so if I want to find the area of this trapezoid, the area of a trapezoid is the area of the base times the average of the two heights. Remember that?
Area.
Okay, so if you have something like this, so if this is your base, and then we want to average our two heights, we'll give you your area. It's a lot right now, I know. We'll have more time tomorrow to walk through things. So base times average of heights of two verticals. So our height is h times, when we average something, we add them together and divide by 2. So 1/2 times, so what's my two heights in this trapezoid? So P or f of x, and then f of x plus h. So the smaller h gets, the better the approximation, right? So if we have a really big, then our trapezoid is not a very good approximation. If it's very, very small, it's going to be a better approximation of the area. Okay, so we have to write down some formulas. So what do we know? So this change of area, we already determined it's right here. So this would be 1/2 h f of x plus h plus f of x, all divided by h. So what happens here? The h's cancel out. So we're using our h's cancel out. So we're left with just f of x plus h, the limit. Sorry guys, I'm as h approaches 0. So 1/2 f of x plus h plus f of x. Okay, so now can we sub in h as 0? Yeah, so what do we get? We get 2 f of x's divided by 2, or just f of x. So what this was trying to prove is that the derivative of our area is equal to our function. And so therefore, to get our area, we take the antiderivative of our function. So that's the conclusion we're trying to make here. So to get the area under the curve is equivalent to the antiderivative of our function. So here's the huge application. Now, if you have a function where you have the equation of the area, the antiderivative would be the volume then. Of our function could give us the area under our curve. It's really cool. Okay, turn the page. Okay, we want to find the area under y equals f of x from a to b. So area under a curve is defined to be the area between the curve and the x-axis.
Wait, so is it like when we're finding this area, or where else are we finding it?
Between 2 points. Oh, yeah, between 2 values. And it's always from the curve to the x-axis. Okay? All right, so since we know the derivative of area is equivalent to our function, we can then say our area is equal to the antiderivative of our function plus c. Now this constant doesn't actually matter. We're going to talk, we don't actually really need the plus c, because if you're finding the area between 2 values, the c's are just going to cancel each other out. Remember, whenever we take an antiderivative, there could have been some constant, right? Because a derivative of a constant is 0, so it doesn't show up here in this function. Now, what we're going to talk about in a second, this guy, and when we're talking about area, doesn't matter. Because he's just going to cancel out, because we're subtracting the 2. Okay, so I'll show you that in a second. So if the area under A would be f of A plus c, and if that's 0, then c would equal to negative f of A. So the initial condition we're saying is 0. Okay, so the initial condition is 0 because we want from this point to this point. So then we can conclude the area A of x, which is what we're trying to find, would be then f of x minus f of A, and finally x equals b. The area under B would then be the antiderivative b minus the antiderivative of A. So basically what this is saying is, if we're thinking of it as, so this whole area, so under B minus under A to 0, okay, would give you this change of area, this area we're looking for, between A and B. Okay, so that's our formula. So how we write this is the area between A and B is given by antiderivative at B minus the antiderivative at A. So this means between A and B. And areas, thank you, always positive. So if it's because if it's under the curve, it actually will come out negative. So if it does come out negative, we take the absolute value. Area is positive. Okay, let's do an example. Okay, so find the area under the curve y equals 2x, folks. If you graph this, 1, 2, 3, 4, 5, 6. Me? Me? Why? I never swore. No, I didn't. No, I did not.
You were like, I was
No, I didn't swear. I don't swear. I don't. I don't swear. I don't swear. I want you to know I do not swear. So what? You heard me. Okay, so let's graph this function first. Y equals 2x. So 1 would be 2, 2 is 4, 3 is 6. I didn't. I would never say that. I wouldn't. I'm not lying. I do not swear. I only swear. Okay. When I fell off my bike and like bloodied myself and I was in midair, there was a profanity that came out. I didn't. Eight. Okay, so we want the area between 1 and 4 underneath the curve y equals 2x. So how we'd write this is the area between 1 and 4 equals the antiderivative of b minus a. Okay, so we need to figure out our antiderivative in order to answer this. Okay, so adding 1 to our power becomes x squared, and then we divide by the 2, so it just becomes x squared. And I'm going to write this for now plus c. Now what happens is if we're subtracting these two, what will happen with our c? It just cancels, so we don't need it when we're figuring out area. Okay, so now we can solve. So our area between 1 and 4, we want to find, so f of 4 would be 4 squared minus 1 squared, which gives us 15 is our area underneath the curve between 1 and 4. That one's not that exciting because it's a straight line. You could probably figure that out yourself. So let's look one more exciting than this. What? Well, it's a trapezoid, right? So, or you could break it up into a rectangle and a triangle. Okay? Okay, find the area of the curve. So let's graph this guy. So y equals, and it's between negative 1 and 3. Negative 1, 1, 2, 3, 4. So y equals 2x squared plus 4 is going to look something like this. Okay, and we want the area between negative 1 and 3. I'm missing like a lot of pens. So this area here. It's a crayon. Crayons are cool. Okay. I'm missing some pens. There's one. I don't know where the other one is. Okay, so we want the area between. Which is our A value? Which one's our B? A and B. Smaller one's A, big one. So we want between negative 1 and 3. And the formula is f of B minus f of A. Larger minus smaller. So f of 3 minus the big F of negative 1. So we need to find our antiderivative of this function. Okay, what are we going to do with our power? Add 1 and then divide by that power of 3. So it'll be 2/3 because we're going to divide by 3 plus 4x. Do we need to worry about plus c? No, so you can just leave it. So let's sub it in. The area between negative 1 and 3. So f of 3, 2/3 times 3 cubed plus 4 times 3 minus 2/3 times negative 1 cubed plus 4 times negative 1. Super cool, hey? Kind of? Maybe not? I don't know. So cool. It is. Okay, 3 cubed, 27 divided by 3 is 9 times 2 is 18 plus 12, 30. Correct me if I'm wrong. That would be negative 2/3 plus or minus 4, negative 14 over 3. Yep, Kate? You got 10 over 3. Yeah, and so then what does that equal to? Final answer? 104 over 3. Is our area. No, because then negative 2/3 minus 4, it's negative 12 over 3. Because you're two negatives there. Okay. All right. Do you want to? Let's do this one together. Determine the area between between the roots of the function. Whoa, we have to figure out what the roots are. Yeah, plus or minus 4. So negative 16's here. So you have to figure out the roots yourself, and we want the area between that. So between the roots. So here. I sense a negative area. You are right. What?
I would argue that the answer is infinity.
Well, it's just between the curve and the x-axis.
How do you know?
Is the area under the curved? I know, it sounds weird. No. So always when we talk about area, I know the wording is not good. It's between the curve and the x-axis.
Oh, right, we did it there.
Right. So here, this is the area we want. Okay, so negative 4 to 4. So the large minus the small. What's the antiderivative of this guy? Not yet. 1/3 x cubed plus minus 16x. Oops. I'm trying to hurry. I'm sorry, guys. So 1/3 4 cubed minus 16 times 4 minus 1/3 negative 4 cubed minus 16 times negative 4. Okay. I'm not doing that in my head. I don't want to. Can I? What do you get? Can I just tell you? You get negative 256 over 3, so our answer would be, you don't have a negative answer. We take the absolute value of that. So 256 over 3. Yes. So this causes a problem. If the area below gives a negative and the area above gives a positive,
What is the area between them?
what do we do if you have some that are below and some above? So say this function y equals x cubed. Okay? And you want to find the area between negative 3 and positive 2. Okay? So we have a problem if that happens. Because things will cancel each other out. Oh, I don't like that color. Okay? So what would I have to do so that we don't get areas canceling each other out?
The radar.
What would you do? No, you don't ignore it. You add them together, so you split it up. So now, in order to find our total area, so then we do the area between negative 3 and 0 plus the area between 2 and 0. Oh, 0 and 2. Shoot. Oh, I did it again. 0 and 2. Okay. So what's the antiderivative of this function? So we add 1 to our power and then divide by that number. So 1/4 x to the 4. Okay, so from negative 3 to 0, who are we going to subtract first? 0 minus b minus a, right? So that'd be, well, here, it'd be 0 minus, so I plugged in 0, it's 0. Negative 3 to the power 4, what would that equal? Divide by 4. Negative 81 over 4? that was the 0 area. 0 to the power 4. Divide by 4. Here, I'll show you plugging it in. I'm plugging it into here. Okay, plus, so 2 would be 2 to the power of 4 divided by 4 minus 2 to the power, or 0 to the power of 2 over 4. 81 over 4 plus 81 over, what's this? 4? Okay, this guy was a negative, but we're taking the absolute value of it. Guys, shh. What does it equal? Which equals 97 over 4. Okay, one last question. We might have almost did it. This one's 0 squared. It's a 0. 2 turned into a 0. Okay, the area under the curve. Okay, guys, please, just one last question. I know I'm asking a lot for me today. At least copy this down. The area under the graph y equals x squared plus ax plus 8 from 1 to 2 is 13. Determine the value of a. Okay, so we know the area between 1 and 2 is equal to 13. So 13 is equal to f of 2 minus f of 1, right? So we need to figure out our antiderivative. What's the antiderivative of this guy? X cubed, and then 6 divided by 3 is 2, plus, so 1/2 ax squared, plus 8x, plus c, which doesn't matter because it'll cancel out. So now we're going to sub it in. So 2 times 2 cubed plus 1/2, a times 2 squared plus 8 times 2 minus, do the same thing with 1. Okay, when you simplify this, in the first bracket we get 32 plus 2a. Really quickly. And in the second bracket we get 10 plus 1/2 a. So, distributing the negative, I'm just going to rush to it. When you rearrange this, you get a equals negative 6. Okay? Sorry that this lesson was so tight and long. Yeah, and then your homework. So that is it.